Again, let's look at the next method of solving linear differential equation of second order with variable coefficient. And this method is called method of exact equation. Yes. So, what does this mean? Or it is also called the method of first integral. Okay, let's see what this actually means. Let's say we have a naught, which is a function of x, d2y by dx square, plus a1x dy by dx plus a2 of xy is equal to f of x. And let this be a, equation a, right? And this is a second order linear differential equation. This would be called an exact equation if there exists a first order linear differential equation. Say for example, b naught of x dy by dx plus b1 of x y is equal to, let's say, g of x, such that, and let's call this as b, such that a can be obtained from b by direct differentiation. So if we differentiate b, we should be able to get a. So here it's vice versa, a, if you integrates to b, b differentiates to a, right? Okay, now based on this, there is a theorem. Now the theorem states that a necessary and sufficient condition for the equation a, remember, this is nothing but a naught. I'll not write of x. It is understood that a naught, a1 and d2 are functions of x. d2y by dx square plus a1 dy by dx plus a2 y is equal to f of x. To be exact is, and this is the condition, d2 a naught by dx square minus dA1 by dx plus A2 is equal to 0. And here A1, A2 and A0 are functions of x. So what this means is that if this is exact, then this condition is true. Or we can also say that for a given equation, if this is true, then the equation is exact. Okay, let's look at both the ways. So let's say an equation is exact, right? So let's say the equation is a, the above what we had written. An equation a is exact. Now what we have to prove? We have to prove that d2a naught by dx square minus d a1 by dx plus a2 is equal to 0, right? So let's take it. So let's take the first order differential equation, right? So let's say b naught dy by dx plus b1y is equal to g of x, where b naught and b1 are functions of x. Now this again is such that a can be obtained by direct differentiation. Basically that means that it is an exact equation, which I already mentioned it here. Okay, now let's differentiate this. So differentiate. So when we differentiate, what do we get? B naught as it is d2y by dx square plus b naught db naught by dx dy by dx plus b1 dy by dx plus db1 by dx y is equal to g prime of x. Now let's rearrange this. B naught d2y by dx square, and this is dy, this is dy by dx, right? So let's combine them. db naught by dx plus b1 dy by dx plus db1 by dx y is equal to g prime of x. Now what we'll do is we'll compare it with the equation A. The equation A is what? A naught d2y by dx square plus a1 dy by dx plus a2 y is equal to f of x. F of x. So let's do comparison pairing. What do we get? We get a naught is equal to b naught, right? This and this, they are both equal. Okay, a1 is equal to b1 plus db naught by dx. This is equal to this, and a2 is equal to db1 by dy, and f is equal to g prime. Now let's do a few additional manipulations. Let's take a2 equal to db1. Now this can be written as, now b1 we know, based on this, b1 is equal to a1 minus db naught by dx. We can bring this to this side. So d by dx of a1 minus db naught by dx. Yes, which means this can be written as dA1 by dx minus d by dx of d by dx of b naught. Now b naught is the same as a naught, so we write a naught. So what we ended up doing is writing a2 in terms of a naught and a1. Yes. Now let's just rearrange this. What happens? Uh, this becomes d2 a naught by dx square, right? So d2 a naught by dx square. If you bring it to this side, it becomes plus minus dA1 by dx plus a2 is equal to 0, right? And this is what we had to prove, right? To prove that this is equal to 0. Okay, that is one. Now let's look at it in the reverse direction. Reverse direction is what? If d2 a naught by dx square minus dA1 by dx plus a2 equal to 0, then the equation, that is a given equation, is exact. Again, what does this mean? How do we prove it? How do we go about proving this? We prove it by coming out with an equation in the form of d by dx of an equation, a differential equation, so that when we differentiate it, we get back the original equation, right? Okay, so let's see how we go about doing that. So we start off with the equation A. So a naught d2y by dx square plus a1 dy by dx plus a2y is equal to f of x. Now what we have to do is we have to write this as a differential of a first order differential equation, right? So let's proceed. Now here, this is already given to us, right? A2, we can write it as A2 is equal to these two terms, we can take it to the other side. So this implies A naught d2y by dx square plus A1 dy by dx plus A2 can be written as dA1 by dx minus d2A naught by dx square. So what I did was I took it to the other side, so it became plus. This I took it to the other side, so it became minus. Right? Is equal to f of x. Now what do I do now? Here I have to write y. Remember y, because a2 y is there. So let's open up that bracket. A naught d2y by dx square plus a1 dy by dx plus dA1 by dxy minus d2A naught by dx square y is equal to f of x. Okay. Now remember this equation, this left hand side plus the right hand side also, the whole thing has to be written in the form of a derivative. D by dx of something should give us this. So how do we do that? If we look at these two, this can be written as d by dx of a1y. Let's do a very quick differentiation. A1 as it is dy by dx plus dA1 by dx y as it is. So this is perfect. Okay. Now what? Now we have this. Now how do we do this? Let's see. Let's take it as, let's write it as a naught dy by dx. Now what happens? A naught as it is d2y by dx square. So one of the terms of the differentiation of this is there. Now the other term would be what? That we just added to the previous equation. Okay, so plus a dA naught by dx times dy by dx, right? So these two combined gives us d by dx of this. Now remember this term I have added here. So this equation has become unbalanced. So we have to subtract it from here so that it becomes balanced again. So dA naught by dx times dy by dx. And what I'll do is I'll take it into the bracket so that this becomes plus, right? So our equation becomes what? Let me take this here. Plus d by dx of a1y minus, again, d by dx of, this can be written as what? Look at it very carefully. You can write it as dA naught by dx times y. Now, whenever you do this kind of tricky things, just reverse the process and see. So dA naught by dx as it is, dy by dx, right? Then again differentiate this. So d2A naught by dx square y as it is. So perfect. And this remains as f of x. Now f of x right hand side doesn't change. Why? Because on the left hand side itself we have done the balancing act. Now all the three are being differentiated, so we can combine them into a single differentiation. So d by dx of a naught dy by dx plus a1y minus dA naught by dxy equal to f of x. Now here y and y are common, so again we can simplify this. A naught dy by dx, we can take it out common, plus a1 minus dA naught by dx y, right? Now f of x also we need to take it inside, not only to the left hand side, not only to the left hand side, but also into this differentiation. But then it changes, so we need to make sure that that is reversed, it gets cancelled. So what we do is minus, because when we bring it to this side minus, we integrate f of x. So differentiation of an integral, they both cancel out, plus c, constant of integration, is equal to 0. So do you notice something? We have arrived at an equation, a first order linear equation, which when we differentiate, we will get back the second order differential equation. And so we can say that it is an exact equation. A is an exact. Okay. So now, based on this, whatever we have done, what we can say is that if the condition for exactness is satisfied, then A can be written as, or rather, integral of A will be A naught dy by dx plus A1 minus dA naught by dx y minus integral of f of x dx plus c is equal to 0. Right? This is not E, this is C. And we can write this as like this. Integral of A is this. And if we differentiate this, we get A, right? So, very interesting. Uh, shall we solve a problem and see how this gets applied? Okay, let's say the given equation is 2x square plus 3x d2y by dx square plus 6x plus 3 dy by dx plus 2y is equal to x plus 1 e to the power of x, right? Now what we have to do is we have to solve it, right? Let's say we have to solve it using exact equation. Okay, so which means what? We have to first check out whether it satisfies the condition of exactness. So for that we require A0, A1 and A2. A0 is what? This 2x square plus 3x. A1 is this 6x plus 3. A2 is 2. Okay, and the condition is what? d2 A0 by dx square minus dA1 by dx plus A2 should be equal to 0. Okay, so second derivative of A0. First derivative would be 4x plus 3. Second derivative would be 4. So 4 minus first derivative of A1, that is 6, and A2. So plus 2. This is what? Minus 2 plus 2 equal to 0, 0 equal to 0. So the condition is satisfied. So we can say the equation is exact. So which means, therefore, first integral solution would be the complete solution of the equation, right? So let's see. A naught dy by dx plus a1 minus dA naught by dx y minus integral of f of x dx plus c equal to 0. Now remember, this is what we had derived, okay? So we do the necessary substitutions and we solve the equation. So a naught is what? A naught is 2x square plus 3x. So 2x square plus 3x dy by dx plus a1 is 6x plus 3, then minus dA naught by dx, dA naught, a naught. So first derivative, so 4x plus 3, so minus 4x minus 3, so 3 gets cancelled, y minus integral of, now f of x is what? F of x is x plus 1 e to the power of x dx plus c equal to 0. Now let's divide the entire equation by 2x square plus 3x. Why? To put it in the standard form. So that implies this gets cancelled. So dy by dx plus, here what do we have? Cx minus 4x is 2x. So 2x and y by 2x square plus 3x. And by the way, here one of the x can be taken common. So 2x plus 3x. So x and x cancels. Minus this, actually we can take it to the other side. So integral of x plus 1 e to the power of x dx. That would be x e to the power of x. Immediately differentiate this to see whether you get this. So this will give you what? Product rule, e to the power of x plus x ex. So you get back this, okay, and divided by this. So that is again x, we can take it out common, 2x plus. Now here when we bring this c to the other side, it will become minus c. So since we normally want plus itself, let's make it c1 by 2x square plus 3x. Now here c1 is equal to minus c. Okay, now it's just a question of simplify. Dy by dx plus 2 by 2x plus 3y is equal to, x and x gets cancelled, is equal to e to the power of x by 2x plus 3 plus c1 by 2x square plus 3x. Okay. Now this is a first order linear differential equation. So therefore we'll use the method of integral factor. So integral factor would be e to the power of 2 by 2x plus 3 dx, which is equal to e to the power of, the integral of this would be what? Log of 2x plus 3. Again, immediately differentiate this. You will get 1 by 2x plus 3 times 2. E and log will cancel out and you're left with 2x plus 3. So we know this would be y times 2x plus 3 is equal to integral of 2x plus 3 times e to the power of x by 2x plus 3 plus c1 by x times 2x plus 3 plus c1. No, c1 is already c2. Now here we can take out this, this and this. So we are left with integral of e to the power of x plus c1 by x plus c2. This is dx is there here. Forgot to write dx. So dx plus c2. And let's integrate this now. We get e to the power of x plus c1 log x plus C2. And on the left hand side, you will have y times 2x plus. So that is the solution to the given equation, right? Because of this, first of all, we can decide in the beginning itself whether it is an exact equation or not, so that we don't have to proceed further at all. It's only once we know that it is an exact equation, we know the first integral exists. So we can proceed further. Okay, I think that's enough for today. Bye for now.